Hi, and welcome to the first of 3 videos on conditional probability. I'll say through, well, this first one is essentially going to just recap our knowledge of probability from year 1, because I think it's useful to do that before you crack into the year 2 stuff. So let's have a quick go through what we saw in year 1. I'm going to run through it ever so quickly. So some notation thing first of all. So we've got that one there, A, U, B. Simply means A union B, and hopefully you can remember from year 1 that means A or B. And on a Venn diagram, that's just the shaded bit there that's in purple. That's in A or it's in B. It doesn't have to be in both. It can be in either. And then that one there, that's A intersection B, which is the AND version. And on our Venn diagram, that's just the bit that's in both. So that's the overlap between the two sets, A and B. On we go. That one, A dash. That one stands, hopefully you remember, that one stands for complement, which just means it's not in A. So again, on my Venn diagram, what I've done is just shaded everything that is outside of set A. So that's not in A. And then this one you may or may not be familiar with, or may or may not have seen before. It does pop up very occasionally. So I've included it. So what we've got here is A, and that means A is a subset of B, which basically means A is entirely within B. Other things we need to be wary of. Firstly is the term mutually exclusive. So if it's mutually exclusive, we've got two sets A and B that don't overlap. So there's no way we can have an event that appears in both. We've got no intersection. So for example, if I was picking a card from a pack and event A was the card is a diamond, and event B would be the card is, I know, a spade. There's no way I can have both. And in that situation, it can't be the same, so they don't overlap. Already just said that. And we've got that A union B, A or B is just simply the probability of A plus the probability of B. Now that might be just simply stating the obvious, but the key part to this is that when they're not mutually exclusive, when we do get an overlap. So now if I include my cards example and I say, okay, what's the probability that a card is a diamond or that the card is a picture card? Because obviously you could have Jack, Queen, King, and so those would be the cards that would be sitting in this overlap, where it was set A, it's a diamond, set B, it's a picture card. Clearly the Jack, Queen, King of diamonds could be both. And that has an impact on our previous form, because previously we had A union B was just A plus B, but because we've got this overlap, if we simply did these two bits here, the bits in the middle would have been essentially double counted, so we have to then take them off afterwards. So now we've got the form that A union B is probability of A plus the probability of B minus the probability of A intersection B. And that's something that you might have to make use of. So that's a formula that you need to make sure that you know. And again, so I was just highlighting that difference between the probability of A union B is different depending on whether they're mutually exclusive or not mutually exclusive. The other term we need to deal with is independence. And again, that's a concept hopefully you'll be familiar with, particularly from GCSE as well. So independence is when the outcome of one event does not affect the probability of the other one. And in that situation, if two events are independent, then the probability of A intersection B is simply probability of A times by the probability of B. And it's a really common exam question. You might get asked to prove whether or not two events are statistically independent, given some information. So if you can show that, if you're given, for example, a value for A intersection B, and you can show that probability A times probability B is that value, then you're saying they're independent. If it's not, then they are not independent. So again, that is something you get asked to do quite frequently within exam questions. Okay, so let's just finish off our recap by looking at an example. So we've got two events, A and B. We've got the probability of A, we've got the probability of the intersection, and we're told they're independent. And we've got to find these things here. So let's start off by drawing the Venn diagram and putting some information on. And when you're working with the Venn diagram, if you're being asked to draw one, which again is something that happens quite a lot in the exam, it's always a good idea where you can start from the middle and work outwards. So what I'm going to do is I'm going to start with this fact here. A intersection B is 0.1. So that's going to go in there. Now that's useful because we now know that the probability of A is 0.4, which means if everything inside my circle is going to be 0.4, that bit there is going to have to be 0.3. Now, that's all we can do at the moment. So let's now have a go at, because we put the information we've given on our Venn diagram, but let's now have a go at part A, and that's where we're going to use the fact that A and B are independent. So if A and B are independent, that we know that is true. So therefore, we can just take our values from up here and put them into our formula. So we've got 0.1 equals 0.4 times the probability of B. Then we've simply got to do a bit of dividing, and so that gives us probability of B. That would be the 0.1 divided by 0.4, and there we go. There's our answer to part A. And on we go to part B. I put hence there because now we're using what's just gone before, because we want the probability that not in A and in B. So not in A, so everything that's outside of A, but at the same time it's got to be in B. So we're looking at this bit here where my cursor is, and so if we look at the fact that we know that B is now 0.25, hopefully we can see that that value there is simply going to be 0.15. And finally part C, so we want A union B, and we want the complement of it, so everything that's not in A union B. So A union B is there, we want everything that's not in that, so we're going to want essentially 1 minus the probability of A union B. And so it's basically everything that's not inside our diagram already, so it's going to be 1 minus all of those bits, which is 0.45. And there we go, that's a quick run through of what we've seen previously. In the next video we'll move on to how we can apply this knowledge and then extend it to involve conditional probabilities.